Hello, everyone. My name is Luca Niccolini from the Traffic Protocols team at Meta. I'm very happy to be here with you today, moderating a Q&A with the speakers of the three talks we just listened to. We have Sri and Krishna from Meta. We have Wang from Google, and Miao is joining us for Alibaba for the Predictable Network talk. Without further ado, let's get the conversation started. I would like to start with Rui from Alibaba. Thank you a lot for your talk. You're joining us instead of Dennis. And I'm curious about the fusion of software and hardware that the talk covers and how that makes performance predictable. It is an interesting approach, and I'm wondering what are the challenges in co-designing software and hardware?
Yeah, so we are transferring from previous protocol-centric network to software-centric network. And the reason behind it is that we want to build a predictable network in terms that we can guarantee the performance, reachability, and the policy control. So that's why we want to enforce our predictable network from the software and also from into the hardware. So into the hardware perspective, we want to make the hardware more standard so we can support better supply chain. So we define the S3 IP standard to align with the ecosystem to provide a white box hardware and then provide a uniform abstraction to the upper layer software like Psi and the Sonic. And then this is why we can build a very generic software to control our network devices. So in terms of software and hardware co-design, we want to make sure that as a cloud provider and operator, we want to enforce the correctness and the performance, and we run the verification tools to verify our software, our network software is correct. And that's why we can enforce the predictable network through this hardware and software co-design.
So thank you. So yeah, would you say, in a few words, would you say that like network programmability is like key for building a predictable network?
Yeah, so that's the requirement we need to build such a predictable performance. One example, like we want to have the precise information from the network to know what's going on inside network. So in this way, the end host can have a better understanding and the network performance and the scenarios and issues and make a better decision. So compared with the traditional solution, like allow networks to figure out what's going on, it's kind of a complex if they don't have like a central knowledge or global view. And we think this is what we call the host and the network co-design. It's a sweet middle ground to allow each host to understand their path and the performance of their traffic going through a network so they can make a better decision. That's the one example that we want to have a programmability inside network and also programmability in the host. And another example I want to mention is about the edge cloud example. So where in the edge cloud, there are lots of heterogeneous devices. And as a cloud provider, we don't even control the hardware and the software. There are devices that are specified by the customer. So in this way, we still want to provide the cloud services like a virtual network and a storage and a DDoS defense services. So how can we do that? And our solution is to leverage those network devices as an entry point of our cloud provider. Then we can provide, we can enforce this cloud services like a virtual network and a DDoS defense, as I mentioned about earlier, into these network devices. So that's why programmability is very important, because we not only provide the network switching function, but also we want to provide this network specific services inside the software, inside the switches. So hopefully in the industry today, we have network programmability to allow us to enforce this policy and services for this cloud computing clusters.
Thanks a lot, Rui. This actually brings me to my next question, this time for Sri and Krishna, about FBOSS and Psi. So Krishna, why did Meta decide to go with the switch abstraction interface, also called SAI? Is the motivation similar to what Rui is talking about, having hardware and software working well together, or are there other drivers for this decision?
Thanks, Luca. Yeah, I think there are a couple of other motivations as well. First one is to capture, like, to have one unified software for across all vendors, because I think about it, if you're going to have one software for every vendor, we'll be rewriting a lot of software. SAI prevents that by using reusability. And the second thing is another major motivation factor for us is to onboarding a vendor is made easy right now. So now that we moved to SAI, what happened was, like, we have one software which runs on both the vendors, and let's say tomorrow we're going to onboard another vendor, so that's made easy right now. Otherwise, what would happen right now is, like, in case we haven't gone with SAI, we'll be writing one platform dependent layer for every vendor. That's more time consuming, more bug prone, and it's also like there's no code reuse there. So that was one of the driving factors for us to go towards SAI.
Yeah, thanks a lot, Krishna. And Shri, still about on the FBOSS topic. Thanks a lot for presenting the way updates are being pushed. I'm wondering, what are the several phases that a bundle goes through before it gets pushed all the way to production, and what kind of tests and validations are run at each step of the way?
Sure. Thanks, Luca. So the hardware tests we talked about during presentation are the ones that run before we start putting into production. But for the canary phase itself, there is no additional test that runs. But because these devices are in production, all the monitoring and tools we use to monitor health of the production network, those start kicking in. So if there is a reachability issue, or if your BGP pairings go down, or if the agent starts crash looping, the standard monitoring that kicks in starts getting exposure, like the code starts getting exposure to that. In addition to that, the canary devices upgrade quite often. So as part of canary testing, we would upgrade and downgrade device in loop multiple times, which gives further exposure. And in turn, further exposure gives us further confidence into the stability of the software before we start pushing it out to wider fleet.
Got it. Yeah, thank you so much. And talking about deployment and safe upgrades, brings me to my next question, this time for Rui Wang from Google. I really appreciated when you talked about how you can upgrade the network when the airplane is flying, so to speak. And so SDN orchestrated upgrades with no network downtimes seems to be a widespread practice today. And I wonder, what are the challenges with that? I'm mostly asking about the reliability aspect, like what are the safety guarantees you put in place to make sure there's no software bug that drains more than it's supposed to, or more than it's safe?
Yeah, thanks, Luca, for the question. I think we need to distinguish control plane. So Google follows a pure play, what is called pure play SDN paradigm. So the devices has no intelligence on them. All the forwarding tables are programmed by the controller that lives outside of the data plane. So in terms of control plane upgrade, yes, there's widely expected that there should be no zero downtime to the data plane. And as you rightly pointed out, I think what's challenging here is you're swapping the entire data plane at the same time and ensuring there's no downtime. So the way to ensure that, and I think one of the I am most proud of is how we converted our fabric from a fully non-blocking CLO topology with the entire spy layer to a direct connect topology, and while all running the service with no application awareness at all. And the way we do this, one, like I said, as I mentioned in the talk, when you reconfigure the topology, the sequencing is really important. Which links do you move first? That's important. The other aspect is the increment. How many links do you move at a time? And this can depend on the traffic, depend on the workload, etc. And we have different layers of defense in-depth to ensure that things don't go wrong. And there are many layers. For example, we guarantee that there's no more than, let's say, 5% or 10%. It's really a tunable parameter. No more than 10% of network capacity is taken down at each time. And there are various systems checking against that. And there are also backstops that continuously monitor the data plane health signals. So if anything goes wrong, right, it will issue the alert and will stop anything that's going on. And
Got it.
For SREs or humans to take a look. So there are just multiple layers to ensure this progresses smoothly. And I like to point out, over the past 5 years, we actually converted the vast majority of our fleet, to this with zero downtime. It was a pretty phenomenal feat that the team had pulled off.
Yeah, thank you. I have another question about Google's fleet, but it's for later. I want to go back for the time being back to Miao from Alibaba with another question about your architecture. So you mentioned that in your predictable network you use a white box single chip network devices. So I wonder if you can elaborate on that. What is the reason to use single chip devices?
Yeah, so our ambition is to use single chip devices and also white box devices everywhere, from data center to backbone WAN network. The reason behind that is it is different with the data center and the WAN. For the data center, because every switch is using BGP to talk to each other, and the vendor also support that quite well. But the reason we want to use a single chip instead of using chassis boxes is because we want to lower the cost, and then we can use a BGP to allow them to talk to each other with this standard inter-devices communication. And the BGP is the one we are using for the data center. And for the WAN, wide area network, we use single chip is using not only for the cost consideration, but also for the reliability, because we were facing some of the issues that happen in our network, that when the device is using other protocols, that we are running very large scale failures, especially for those legacy protocols like ISS and OSPF, those kind of things. And then they have their different vendor may have different implementation, and they maybe in some scenarios will trigger their bug. And when the bug happens, will cause a very network downtime. So that's why we want to have a single chip device, and to allow them using standard communication protocol to talk to each other. For the one we are using SRv6, it's an IPv6 based segment routing. We want to have a vendor to implement correctly using the same interface and abstraction. So that's why as a cloud operator, we can verify, specify, and control our network in a more reliable way and a more performance aware way. Thank you.
Yeah, thank you. And speaking of multiple hardware solutions or single hardware solutions, I have a question for Krishna about FBOSS. And you mentioned in the talk that hardware tests were run also by the vendors. So we share these tests through open source. And this is a question that comes from the audience as well. Do these tests, how do we make sure that the tests that the vendors run provide enough coverage for us for the SDK to qualify, and how do we manage that?
Okay. Thanks, Luca. So first of all, we have around 1,000 test cases open source today, which includes both cold boot and warm boot test cases. This includes all the way from basic software and hardware initialization, from L2 forwarding, L3 routing, ACLs, quality of service, and line rate traffic test cases. So all these things are open sourced so that vendors can run it. And to answer your question, yes, they do provide enough coverage, because this acts as one of the gating factor for us to even for the vendor to release the SDK in the first place. So they run these test cases through open source, and then they provide the results to us to make sure that what test passed versus what failed. And that acts as a gating factor for us to even to pull in the SDK to integrate to Meta's fleet.
Yeah, thank you. And the question from the audience was, where can we find these test cases? And I guess they're on the GitHub repo.
Yes, it is indeed. If you can Google like FBOSS agent GitHub, so that should provide like all the test cases being open source today.
Thank you so much. And Shri, still on FBOSS, what would you say is the average time that it takes for a new feature, like a major update to be rolled out at Meta today?
Sure. So I guess the answer is it depends. It depends on whether it's a feature that can be enabled by warm boot. By warm boot, we mean without causing traffic disruption. If the answer is yes, if it can be enabled without causing traffic disruption, then the tooling doesn't really put a constraint. You can go very quickly and update the fleet. Usually we want to slow down and pace it in order for us to make sure that it is very safe to roll it out. So depending on monitoring and confidence level in the feature and how critical it might be, which piece it belongs to, we might choose to slow it down. But the tooling doesn't prevent us. We can go very quickly if we like. It's a different story if it's a feature that cannot be enabled without causing traffic disruption, because that requires the so-called disruptive upgrade. And there the story is that if the device we are upgrading is connecting to a rack switch, then we don't have redundancy on rack switches, which rack switches being the switches that connect directly to servers. For those, because there is no redundancy, draining production traffic of those before you can upgrade, that can take time. But if it's not a rack switch, then we have redundancy. So although it takes away redundancy for some time, it's a short maintenance window that we can schedule and upgrade very quickly. So which is the reason I said it depends. Like for disruptive features, it can take longer on rack switches. For non-disruptive, we are really constrained by our desire as to how quickly we would like to go and update. Tooling doesn't block us.
Yeah, thank you. And it's still probably an order of magnitude faster than before FBOSS came to be.
Absolutely. Yeah, absolutely.
Yeah. So to circle back and go back to Rui Wang, I'm curious about Google Network. And, from your talk, something that I think I got is that Google's data center network seems to be highly heterogeneous. Like there's a lot of different technologies that coexist. And I'm curious, like, if there's anything you can share about how did that came to be, and how do you manage this complexity?
There are two kinds of heterogeneity in our data center. One, like you pointed out, is the device heterogeneity. So we allow coexistence of multiple network generations in the same fabric. For example, we may have 100 gig, 200 gig, and 400 gig coexisting in the same fabric, interoperating. The other dimension of heterogeneity comes from the workload side. So Google, every fabric, data center fabric is shared. So it may run real-time applications to batch workload to ML. So to account for the first dimension of device heterogeneity, we mainly work at it from three directions. One is the optics that were plugged in to the electrical packet switches need to be able to interoperate, at least across 3 generations. And then the optical circuit switch layer, which the nice thing about it, as I pointed out in the talk, is it's data rate agnostic. So it becomes part of the building infrastructure. So they don't need to be upgraded as you upgrade the rest of the network. Third is when you have this heterogeneity, we have to bring in intelligent reconfigurable topology to manage this. I've pointed out a toy example in the talk by leveraging. First is how do you align you need to align your topology to your traffic communication pattern. And second, you can leverage the existing capacity in the network to serve as your speed conversion capacity.
Yeah.
So these are the building blocks that we deploy to manage this heterogeneity.
Yeah. Thank you so much. We could talk about these topics for a long time, but our time is up for today. I want to thank all the speakers and everyone that joined us for this panel. Thanks a lot again. And we have 2 more presentations coming up next, followed by another Q&A session. Thanks a lot for being here with me today.